Imagine passing a massive 3D model or a million-node neural network into a simple function. The computer must decide exactly how to deliver that data. By default, C++ enforces strict local boundaries. Every function operates inside its own sealed sandbox, isolated from the rest of the program. To get data across that boundary, the compiler creates a completely independent duplicate of the original information to place inside the new function. For a standard integer or a simple Boolean, this copying process is nearly instantaneous. But for heavy, complex data objects, this default behavior introduces a critical vulnerability. Every time you pass a sprawling binary tree into a function, forcing physical duplication destroys execution speed and rapidly exhausts your available stack memory. We need a mechanism to manipulate these massive objects across function boundaries without ever triggering that duplication event. To architect high-performance systems, you have to explicitly bypass the default. You must master memory and direction to safely pierce those boundaries. Let's set up a test environment to see exactly how this works. We'll start with a primary function containing 3 standard integer variables, a, b, and c, all initialized to the value of 10. We want to pass all 3 of these variables into a secondary function called dummyUpdate, which is designed to simply add 5 to whatever input it receives. To understand the mechanics, we must look directly at physical computer memory. Here is our main function stack frame, mapped out with our memory blocks holding 10 at specific hexadecimal addresses. When dummyUpdate is called, the system spins up a completely new, isolated stack frame. We will pass our variables using passByValue, passByReference, and passByPointer. Mapping how the RAM reacts to each of these methods reveals the physical logic governing each call. Visualizing this stack behavior provides the mental model needed to manage memory and avoid segmentation faults. Let's begin with our first variable, a, passed by value into the local parameter m. The compiler allocates a completely separate memory block on the right side of the stack, generating a new hex address. The original integer 10 is physically copied across the boundary and dropped into m. When the operation runs, m successfully increases to 15. Notice our original variable a. It remains completely untouched at 10. The addition only occurred within the sealed local scope of the duplicate. If a had been a high-resolution image file instead of an integer, the processor would have wasted significant cycles cloning the entire file into a new memory location just to read it. PassByValue guarantees strict safety by isolating changes, but its mandatory duplication mechanism makes it unscalable for mutating massive data objects. Now we shift to our second variable, b, which we are passing by reference into the parameter n. A reference acts as a compiler-level alias, an alternative name for something that already exists. Declaring this reference triggers no new memory allocation on the stack. No new block is built, and no hex address is generated. Instead, the reference shares the exact physical memory space, pointing directly back to b. When we add 5, the operation travels that line and directly modifies b to 15. The mutation succeeds with 0 duplication. C++ enforces that a reference cannot be created unless it points to valid, pre-existing memory. It cannot hold a null value. References provide a highly optimized solution for large structures, granting direct access without the duplication overhead, all while maintaining strict compiler safety. Finally, we address variable c using callByPointer. To do this, we must pass the exact memory address of c using the addressOf operator. Unlike a reference, a pointer is a completely distinct, separate variable. It demands its own stack space and receives its own unique hex address. But instead of holding a standard integer, it stores the memory coordinates, the literal hex address, of our original variable c. To interact with the data, we use the dereference operator, telling the compiler to go to the address the pointer holds. When executed, the system reads the stored address, crosses the scope boundary to locate c, and applies the math, bringing it up to 15. This is powerful, but a pointer can legally be assigned a null value, meaning it points to nothing at all. This requires careful checking to avoid crashing your program. Pointers conquer the local scope bottleneck by explicitly mapping memory locations, giving you absolute, highly dynamic runtime control in exchange for an allocation cost and added developer responsibility. If we check the final state of our primary variables after the update finishes, the execution history is clear. Variable a remains isolated at 10, while B and C were successfully targeted and mutated to 15. To codify when you should use each mechanism, we can look at this comparison matrix across 3 structural metrics. Notice the stack allocation requirement. Values demand heavy duplication. Pointers require a small allocation just for the address, but references cost 0 extra memory. This leads directly to a universal performance rule. Large, complex data types should almost always default to being passed by constant reference. Adding the constant keyword guarantees the data is read-only, preventing accidental mutations, while the reference mechanism completely eliminates the stack allocation penalty. True algorithmic optimization requires knowing exactly how to maneuver your data structure without creating redundant footprints in RAM. You might wonder, if references are safer and cheaper, why do pointers exist at all? References are rigid. Once assigned, they cannot be changed. Pointers are dynamic. You need them to continuously reassign links between nodes in a list, or to handle optional parameters where legitimate null state is required. The guideline is straightforward. Use references as your default for safety and speed, and deploy pointers strictly when you need dynamic spatial control. Applying these rules establishes a copy-free data flow throughout the application. Directly managing physical stack memory allows for the construction of C++ systems that prioritize precision and resource control.